Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to learn thermal stresses or temperature stresses. What is thermal stresses? Thermal stresses means if the temperature of a body changes by increasing or decreasing its body's temperature, its geometry also affected accordingly or correspondingly. If these changes are checked, then the stresses developed in the body are known as thermal stresses or temperature stresses. Corresponding to those stresses, the strains are known as temperature strains or thermal strains. Temperature strains or thermal strains. Suppose we consider, if you consider your body by lowering the temperature or increasing the temperature, there will be the temperature produces expansion or contraction of materials and results the thermal strains and thermal stresses. Now here the temperature is increased here. Now in this session the temperature is increased. The temperature causes here increasing the dimensions both in x, y and z directions. Elongation is increased in x and in y direction and also in z direction and also in the direction z axis. So the body's dimensions are changed because of the changing the temperature. Or change in temperature produces. If we consider a copper material, if we increase the temperature, then there will be deformation. The same material under lower temperature at negative temperature, the body deformation reduces. So there is a decrement in dimensions. But either increasing the temperature or decreasing the temperature is nothing but changes in temperature produces expansion or contraction of materials. Because of changing the temperature, the expansion or contraction is taking place. The stresses developed by temperature is known as the temperature stresses or thermal stresses or temperature strains or thermal strains. Now, the thermal strain epsilon T is proportional to temperature change. The epsilon T equal to alpha times change in temperature T2 minus T1. This change in temperature, that is the thermal strain, that is delta T, thermal strain equal to alpha times T2 minus T1. The delta L equal to alpha times T2 minus T1 into L. And the epsilon T, that is thermal strain equal to delta L by L. That is alpha times T2 minus T1 into L by L. That is alpha times T2 minus T1. This T2 minus T1 is known as the change in temperature delta T. So, if the sign convention we follow here, thermal strains, when there is expansion, it is positive, and it is contraction, it is known as a negative. If the thermal strain is positive, means there is expansion. If thermal strain is negative, that means there is contraction. Here, what is alpha? even though explained here, alpha means coefficient of thermal expansion or coefficient of linear expansion thermally. This T2 is the temperature is raised. T1 is the initial temperature. T2 is the final temperature. The difference of final and initial temperature is known as temperature change. We studied now here thermal strain, that is alpha times delta T. What is thermal stress? The thermal stress generally when the initial load, when the axial load is applied, then the strain equal to stress over Young's modulus or modulus of elasticity, that is sigma by E. Now here we know that epsilon T, that is thermal strain, is alpha times delta T. Now from this basic formula we can derive the thermal stress, that is sigma equal to epsilon times E. Then sigma equal to E times epsilon, that is alpha T, that is thermal stress equal to E times alpha times delta T. This is the thermal stress. So by this, using the stress, the thermal stress can be calculated by using this formula. Thermal stress can be calculated, and also thermal strain can also be calculated. We can see in this figure the initial length of the bar is L. By increasing the temperature, the length is increased, that is the delta T. What is the delta T? That is change in temperature, delta T. So this increasing the strain caused by, here it is the thermal strain. When the load is applied and also temperature is increased, then the total strain equal to the strain due to the axial load plus the strain due to temperature. That means the sum of linear strain plus temperature strain is known as the total strain. Now here the block of material subjected to an increase in temperature, as already discussed, but some of the points we can discuss more. That the material here we consider is homogeneous and isotropic, and the temperature increase delta T throughout the block. Delta T is throughout the block. So we can increase any dimension of the block by multiplying the original dimension by the thermal strain. That is epsilon T, thermal strain, that is change in temperature, increase in dimension due to temperature is delta T equal to epsilon T times L. That means epsilon T equal to delta T by L. What is this delta T by L? Then delta T equal to epsilon T times L. Epsilon T equal to alpha times delta T multiplied by L. This indicates the temperature and the displacement relation. This formula shows the relation between the temperature and displacement. Delta T equal to epsilon T times L, that equal to alpha times delta T times L. Now, when there is the combination of stress and also temperature in that environment, the total strain is equal, thermal stress, the total strain, thermal strain equal to sum of the total strain equal to sum of strains, that is lateral strains and also thermal strain. It is divided into two components. That means here one more thing is that the total strain in your body experiencing thermal stresses, the total strain in your body experiencing thermal stresses divided into two components, that is stress due to stress strain due to stress and also strain due to the temperature. It is a sum of epsilon sigma plus epsilon T, temperature. The first component is strain due to stress. Second component is strain due to temperature. The total strain equal to strain due to normal stress, that equal to sigma by modulus of elasticity, plus the strain due to temperature is alpha times T. This is the total strain. Now, lateral strains will be occurred by the axial load. If the body is free, if we increase the temperature, there will be deformation, but there is no stress occurred. The stress will be occurred if we check the deformation. Increase the temperature T, then instead of moving out of the restriction, we are compressing it, we are checking it, the deformation. That causes to increase the stress in the body. That stress developed due to temperature, by checking the deformation, then those stresses are known as thermal stresses, and corresponding strains are known as the thermal strains. Thermal stresses and the corresponding strains are known as thermal strains. This thermal stresses or thermal strains will be occurred when there is a checking. Even though increasing the temperature, it is freely elongating, there is no stress. Okay, the stress will be developed when there is obstruction. Okay, little bit understanding psychologically, when the person is expecting something, those expectations are not fulfilled, it causes the stress in the body. If those expectations are fulfilled freely, whatever is desiring, it is happening, then there is no stress in your body. That's why if there is no expectation, then there is no stress in your body, whatever happens maybe. That is the difference. But in the case of material, without applying the load, then there is no stress. If load is applied, then deformation is going to take place, no stress. The load is applied, there is a checking point for deformation, then the stresses will be developed. So stress is nothing but it is the resistance to deformation, resistance, inertia to deformation. Then the stress occurs in the body. Now here we are going to study the thermal stresses for tapering section and the composite bars. Here we have considered the tapered section, where L is the length of the bar, D1 and D2 are the diameters of bigger section, bigger end and smaller end, and T is the change in temperature, and alpha is the coefficient of thermal expansion. For this case study, the change in under the load applied under the compressive load, then the delta L equal to 4PL by pi E times D1 D2, and due to expansion, due to temperature expansion, okay, then it equal to delta L equal to L alpha T. So the compressive due to contraction and expansion, if we equate, then there is no change in length. Then 4PL by pi E equate 1 and 2, 4PL by pi E D1 D2 equal to L alpha T. From that P equal to L alpha T times pi E D1 D2 by 4L. So the maximum stress, this is the load we calculated. The maximum stress equal to load by area. The maximum load by area, that maximum stress equal to this P by area pi D2 square by 4. Then sigma equal to, substitute here, this P substitute back in this equation, then we can get it. Then sigma equal to alpha T E times D1 by D2. So this is the stress, maximum stress caused due to temperature in a thermal stress. The maximum thermal stress equal to alpha Te times d1 by d2. This is the formula we derived. Now another case study. What is the type of thermal stresses in bars? From Hooke's law, here there are bar is here one in this figure. It indicates BC is the circular cross section bar. It is subjected to a axial load P, and there is a deformation of delta, and L is the original length. After applying the axial load, the deformation is delta. Now from Hooke's law, the stress is directly proportional to strain. Then stress equal to the constant of proportionality times strain. That constant of proportionality is known as modulus of elasticity. Sigma equal to E times epsilon. Then epsilon equal to stress by modulus of elasticity. This modulus of elasticity equal to modulus of elasticity is E, and stress substitute in the place of stress P by E, that's P by AE. Now from the definition, strain equal to change in length by original length, delta by L. Then this epsilon substitute, then delta equal to PL by AE. So this formula, suppose if you are applying for variable cross sections or variations in loading or different material properties, then the formula becomes sigma delta equal to sigma times I equal to 1 to n PI by AIEI. This is the formula. If it is only uniform cross section, then delta equal to PL by AE. If there are variable cross sections, delta equal to P1 L1 by A1 E1 for different material properties and different cross sections and different lengths and different loads. P2 L2 by A2 E2 and so on. Then the sum of this formula is written as, in simplification, sigma equal to I equal to 1 to n Pi Li by Ai Ei. For different sections. So this Pi Li Ai Ei, these are all variables. That means this is the total deflection of at variation of the loading, variation of the length, variation of cross sections, and variation of materials. At different materials, the total deflection formula is sigma I equal to 1 to n times Pi Li by Ai Ei. Okay. Next case is the thermal stresses or temperature stresses in composite bars. Here the two bars are the bar 1 and bar 2, the material 1 and material 2, having thermal expansions, coefficient of thermal expansions alpha 1 and alpha 2 is length is L. Suppose the temperature is increased, then the material 1 is deformation is more, elongation. The strain is more than the material 2, so strain. Now, in order to make it equal, what to do? We have to make it neutral. It's the middle, that is middle portion. So there is, if we abstract, then if we abstract in the middle is the middle cross section neutral, then there is a compression in the material 1. You have to apply compressive load, and there is a tensile load in the material 2. Tensile load, that means tensile stress, positive thermal stress acts. Deformation, you have to make a deformation material 2 and contraction in material 1. The contraction for material 1 is considered as negative, and deformation or extension in material 2 is considered as positive. How to calculate these thermal stresses? So these are the free expansions due to end fixing force. The strains or expansions are L alpha 1T and L alpha 2T. Okay. And in the case due to end fixing force F, the decrease in length of the bar 1 is FL by A1 U1, and increase in bar 2, that equal to F2 L2 FL by A2 E2. Now at equilibrium, the strain, both are strains only, L alpha 1 T. Here L alpha 1 T is maximum minus FL by A1 E1, that equal to L alpha 1 T is the maximum. That is, we are making it, that is how much we have to subtract it to make it equilibrium. For both the bars you have to make it equilibrium. L alpha 1 times T minus FL by A1 E1, that equal to L alpha 2T plus this portion, then it becomes equilibrium, FL by A2 E2. So after simplifying further, that F equal to 1 by A1 E1 plus 1 by A2 E2 equal T times alpha 1 minus alpha 2. Then what is the stress equal to? Stress equal to force by area. This F by A, if you substitute, then sigma 1 and sigma 2, the thermal stresses observed in the material 1 equal to, that is T times alpha 1 minus alpha 2 times A2 U1 U2 by A1 U1 plus A2 U2. And sigma 2, the thermal stresses in material 2, that is T times alpha 1 minus alpha 2 A1 U1 U2 by A1 U1 plus A2 U2. Here, what is T? Where is the temperature? What is temperature difference, delta T? And what is alpha 1? Coefficient of thermal expansion of the material 1. Alpha 2, coefficient of thermal expansion of material 2. A2, area of cross section of material 2. E1, modulus of elasticity of material 1. E2, modulus of elasticity of material 2. So these are the knowns we have to know it. So these are the thermal stresses of a composite bar. If the composite bar means the different materials we have combined for the same applied load and the same length. Here we consider F and L are both are same. But by changing the temperature, there is increase in area of cross section. Increase in area of cross sections or increase in lengths, increase in strains. There will be a variable in strains. Because the coefficient of thermal expansions are different, therefore the elongations are also different. But you have to make it uniformity, otherwise the non-homogeneity carrying load affects the material and also components because of this coefficient of thermal expansion. So we have to fix for a uniform length. That uniform length, for fixing both the lengths, suppose it is more, then we have to reduce it. If it is less, we have to increase and make it equilibrium. That equilibrium equation is, in this case, for both the materials, that is L alpha 1 T minus FL by A1 U1 equal to L alpha 2 T plus FL by A2 U2. Here for material 1, the thermal strain is more. For material 2, thermal strain is less. So make it equal thermal strain minus linearly FL by A1 U1, that equal to thermal strain of material 2 plus FL by A2 U2. So in that manner, the stresses sigma 1 and sigma 2 are calculated. These sigma 1 and sigma 2 are known as thermal stresses of material 1 and material 2. Let us see the example. Here it is from the reference from, here I mentioned reference. Here the reference is from Strength of Materials book. A steel bar is placed at the two copper bars, each having the same area and length. As steel bar is 20 degrees, at this stage they are rigidly connected together at both the ends. When the temperature is raised to 320 degrees Celsius, the length of the bars increased by 1.5 millimeter. Determine the original length and the final stresses in bars. So these are the modulus of elasticity and coefficient of thermal expansion of both the materials are given. Now the copper here, in this case, the copper thermal conductivity is more, that's why it is increased. And whereas steel, it is less in comparison to copper, that is thermal strain is low. Now how to make it equal? These are the free expansion. So if you consider area of cross-sectional area of steel bar is A and cross-section of the two copper bars 2 times A to A. Now free expansion of steel bar, that is alpha T2 minus T1 times L, where it is alpha C times T2 minus T1 into L. Now this, we have to be in equilibrium, we have to maintain equilibrium, we have to let delta be the actual expansion of each bar. Then this delta E is in the middle of both the copper and the steel. That is alpha S, that is a steel thermal expansion is lower than the delta and also lower than the copper. Now what are the equations? So the steel is, we have to make it tensile and the copper should be under compression. Then the total stresses we have to calculate it in steel and copper. Then before that the strains, the total strains in copper and steel equal to, make it sum of these two, then alpha C minus alpha S into T2 minus T1. Substitute alpha C coefficient of thermal expansion of copper and steel and also temperature variation. The final is raised temperature is 320 and initial temperature is 20. This is the value. Substitute in the place of, these are the EC means thermal strain in copper, ES steel, strain in steel. That is nothing but sigma C by EC, ES equal to sigma S by ES. Substitute, then it is 0.00165. Now another equation is that for maintaining equilibrium, the strain, that is sigma S into AS, the load remains the same. That is pull in steel equal to push in copper, that is sigma S into AS equal to sigma C into AC. From this sigma S into what is AS is A, sigma C times AC is to A. Then sigma S equal to 2 times sigma C. Now we know the equation EC plus ES equal to just 0.00165. In the place of EC, substitute sigma C by EC, modulus of elasticity, and in the place of strain S, sigma S by ES, that equal to 0.00165. Now we know that sigma S equal to 2 times sigma C. Sigma C by EC plus 2 times sigma C by ES equal to 0.00165. From this we know the EC value and ES, modulus of elasticity of copper and the modulus of elasticity of steel are calculated, are known, and we can calculate sigma C, the thermal stress in copper material. After knowing sigma C, if you substitute in this equation, then sigma S, thermal stress in the steel, can be calculated. This is the what form we have done. Sigma C by, that is modulus of elasticity of copper is 110 times 10 power 9 to sigma C S equal to 2 times sigma C by ES 220 times 10 power 9. 0.00165. So simplification, after simplification and calculation, the value of sigma C equal to 90.75 mega Newton per meter square. Then sigma C equal to 2 times sigma S. 2 times sigma S equal to, sigma S equal to 2 times sigma C. This is sigma S equal to 2 times sigma C. So sigma S value comes if we multiply the value of sigma C by 2, then we can get it, the value of thermal stress of steel, that is 181.5 mega Newton per meter square. So these are the one objective thermal stresses. Then another one is that the original length. What is that? L. So from this equation, that is epsilon C in copper equal to alpha C times T2 minus T1 minus epsilon. Okay. Then alpha C we want what we need here? That is here epsilon equal to alpha c times T2 minus T1 minus epsilon c. We know the alpha c, T2 and T1, and what is epsilon c? Epsilon c is sigma c by EC. We know sigma c value calculated, and EC given data. Alpha c coefficient of thermal expansion of the copper, temperature change 320 minus 20, that is 300. Then epsilon can be calculated. That epsilon value calculated is 0.004425. Then what is epsilon equal to? Delta by L. Then that equal to given that delta equal to, what is delta equal to? Epsilon times L. We know that epsilon is the value of epsilon, that is delta equal to 1.5 millimeter. That is 1.5 converted into meters, that is 0.0015. From this, L equal to delta by epsilon. The delta is 1.5 into 10 power minus 3 by epsilon is 0.004425. Then the value comes, it is 0.339 meters. That is nothing but 0.339 meters. We got it L. 0.339 meters. That L, original length of the bar for all is 0.339 meters. So let me summarize. In this session, we have studied what is the thermal stress and definition of thermal strain, and also explain mathematically what is thermal stress value and thermal strain value, and case studies the thermal stresses of variable cross section and the thermal stresses of variable materials, variable cross sections and variable loads. What are the stresses or total deformation, and also how the thermal stresses occurs in composite bars. And we solve the problem for the case of composite bars. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.